Good morning, everyone. When we conduct high-precision geodetic surveys using advanced instruments like total stations or global navigation satellite system. The receivers, we are attempting to map the physical features of the Earth with millimeter-level accuracy. However, the first rule of geodetic science is that no measurement is ever perfectly exact. This brings us to our first major concept, the sources of errors which stem from specific identifiable origins in the field. In geodetic surveying, these errors arise from the inherent physical limitations of our equipment, such as optical misalignment in a total station or clock bias in a GNSS receiver. They also stem from unpredictable environmental changes like atmospheric refraction bending a laser beam or signal interference through the ionosphere. Furthermore, human limitations during instrument setup and simplified mathematical models that fail to perfectly replicate the Earth's curved geometry all contribute to these errors. Understanding exactly where these discrepancies originate is our crucial first step, because we cannot hope to manage or minimize spatial uncertainty until we map out its physical causes. Types of error and the nature of error. Once we acknowledge these various spatial and atmospheric sources, we quickly realize that not all surveying errors behave the same way, leading us directly into the nature and classification of errors. To make sense of the variations in our field data, geodetic engineers divide errors into three distinct categories, which are gross, systematic, and random errors. Gross errors are essentially human blunders, such as miskeying a point ID into the data collector or setting up the total station over the wrong control monument. Systematic errors are predictable, persistent biases that consistently skew our data in one specific direction, such as a GNSS antenna height that is incorrectly entered, causing every single measured elevation to be exactly 10 centimeters too low. Random errors, on the other hand, are the unpredictable, chaotic fluctuations that bounce up and down without a clear pattern, like small wind gusts vibrating the tripod or slight variations in satellite signal tracking. By categorizing our surveying errors into these three distinct families based on how they behave, we can move past simply acknowledging that our coordinate data is imperfect and begin developing targeted strategies to tackle each type of error individually. Eliminating gross error during fieldwork. Now, when we look at these three categories, the most immediate threats we must eliminate during the actual data collection phase are gross errors. It is a fundamental rule of geodetic measurement that our final data set cannot be affected by gross errors if it is to be considered legally and structurally valid. Because gross errors are caused by human carelessness, such as misreading a leveling bubble, targeting the wrong prism reflector, or forgetting to tighten the tripod legs, they do not represent the actual physical geography of the land. Instead, they represent a failure of the field crew's quality control. Therefore, through strict adherence to rigorous field protocols, double-checking our instrument setups, and utilizing automated target recognition features on modern total stations, we ensure that these blunders are caught, flagged, and completely removed from our data before we ever begin our final network adjustment. Handling systematic errors via calibration. Once we are confident that all human blunders have been eradicated and our field data is clean of gross mistakes, we are left confronting the more subtle, built-in flaws of our equipment, known as systematic errors, which we fortunately handle through calibration. Because systematic errors are consistent and predictable, meaning the total station or GNSS receiver is consistently reading too high or too low due to a manufacturing defect or physical wear. They follow predictable physical and mathematical laws. This predictability allows us to fix them by comparing our field instruments against an absolute, trusted baseline standard. For instance, if we take a total station to a certified electronic distance measurement baseline and its laser consistently reads 2 millimeters long over a known distance, we have successfully identified a systematic instrument constant bias. Through routine baseline calibration and software configuration, we can program the instrument to automatically subtract that exact bias from every future shot, effectively neutralizing the systematic error before it can corrupt our survey network. The reality of reaching pure random error. Finally, once we have successfully exercised total human care to eliminate gross errors, and we have meticulously tuned our total stations and GNSS receivers through calibration to wipe out systematic bias, we arrive at the ultimate boundary of geodetic science, a state where the only errors that remain are random errors. This is the baseline of physical reality, representing the unavoidable noise of the universe caused by microscopic, uncontrollable variables like minor thermal expansions in the total station chassis, slight electronic noise inside the GNSS antenna, or sudden minute changes in atmospheric pressure. Because these random errors are completely unpredictable and equally likely to push our coordinate positions slightly too far north or slightly too far south, they naturally form a symmetrical, bell-shaped curve known as a Gaussian distribution. Since we can never calibrate away these microscopic, random atmospheric and electronic fluctuations, the only way to conquer them is through the power of advanced statistics, by taking a large number of repeated observations and performing a mathematical least squares network adjustment, allowing the random ups and downs to cancel each other out, and leaving us with a final coordinate dataset that is as close to the absolute truth as humanly possible. That's all for this chapter. Thank you.